Hello and welcome back to Mech Zone. In the previous lecture, we have started off with the chapter on vibration analysis, and we have also solved some numericals where we were supposed to find out the natural frequency of the system, and we did it by energy method and we also did it by the torque method. Now we will discuss one important numerical which is based on the torque method, but this time this system, instead of being in the vertical direction, the spring mass system has been given in the horizontal direction. For example, we have been given this type of system such that the mass of this rod or beam, you can say, is m, so weight is mg in this direction. Here we have a spring of stiffness s. Okay, so initially we will find out, or we will observe, that this rod is getting deflected, or this rod is getting a little bit of deflection by, say, an amount xi. So initially there would be sxi amount of force in this spring. Okay, and this deflection is actually taking place by a small angle, say theta. Now we will apply all those rules, all those procedures similarly in this equation. Okay, so what we did is we displaced this system by an angle theta. Okay, now since this system was displaced by an angle theta, okay, so I theta double dot will act in the opposite direction according to the D'Alembert's principle. Okay, and here we see that the torque, because of mg, has been cancelled by sxi torque. Okay, so we are actually considering the torque about this hinged point, and the torque because of this mg about this point has been cancelled by the sxi about this point. So we are not going to include mg in our final expression. Okay, and what would be the torque because of this spring? It will be acting in this direction such that it is equals to SL theta and multiplied by L. SL theta is the force in the spring, whereas SL theta into L would be the torque. Okay, so if we find out the natural frequency by using these parameters, I theta double dot plus SL square theta is equals to 0. Okay, and here we see that we have already calculated in the previous session also that the value of I came out to be ml square by 3. Okay, so if we substitute the value of I is equals to ml square by 3 and make the coefficient of theta double dot as 1, then we would find out omega n is equals to under root SL square upon ml square by 3. So this would come out to be under root 3s by n. Okay, so this is actually coming out to be the natural frequency of this system, and we see that the torque because of this mg would be cancelled by the torque which would have been produced by s into xi. Okay, now we will start with the next topic, that is torsional vibrations. Okay, we will now start with the topic, that is torsional vibrations. What is actually happening here is we are having a shaft like this on which we have been given a rotor. Okay, we have been given this rotor such that this is actually the axis of the rotor. This is the rotor that has been given. This is the axis of the rotor, and it is having, or this is actually called as the polar axis. Okay, and this is having area moment of inertia about the polar axis, say it is J, and G is the modulus rigidity. Okay, so what we are doing is we are displacing this rotor by an angle theta in this direction such that ST into theta would be in this direction, where ST is actually the torsional stiffness and ST is equals to GJ by L, where L is the length of this rod. And Since the system is being displaced in this direction, then the direction of D'Alembert's would be in this, that is I theta double dot. Okay, and the rotor is having the inertia I. Okay, so I theta double dot plus st theta would be 0. Theta double dot plus st upon I theta is equals to 0. So omega n simply becomes st upon I. Okay, it simply becomes st upon I. So if we now we will discuss a very important concept of node in this example. Now node is a point where we are having zero vibration, and since this point is a fixed point and hence it becomes a node, and we will get the distribution like this. So the vibrations are actually decreasing as we are moving in the upward direction, and these vibrations are actually reducing to zero at the fixed point, which is called as the node point. Okay, and there is a node point, and the node point is that if the shaft is also having some inertia, say it is given as I shaft, so omega n would be simply equals to st upon I plus I शाफ्ट अपॉन 3. जैसा हमारा शाफ्ट का अगर मास दिया, वहां पे अगर मास दिया होता था स्प्रिंग का, तो मास ऑफ द स्प्रिंग को भी 1/3 ले लेते थे. यहाँ पर भी सिमिलर टाइप ऑफ कॉन्सेप्ट है. इस फॉर्मूले को हमें याद रखना है. ओके, एंड इट डज रिप्रेजेंट द सेम एज द केस अर्लियर. जो अर्लियर केस वैसे ही लगभग काफी मिलता जुलता फॉर्मूला है, बस यहाँ पे आई शाफ्ट का 1/3 हमने ले लिया है. ओके, सो ये हमारा पॉइंट है रोटर में, जिसको हम कहते हैं नोड. और नोड जो है एक्चुअली यहाँ पर आप देख ही रहे हैं फिक्स्ड पॉइंट है, एंड यहाँ पर हमारा होगा नो वाइब्रेशंस. ओके, हियर वी विल हैव नो वाइब्रेशंस. ओके, नाउ इसी से रिलेटेड हमारा जो नेक्स्ट इसमें टॉपिक है, दैट इज टू रोटर सिस्टम है. नेक्स्ट हमारा टू रोटर सिस्टम. तो आपने अगर अभी तक हमारा चैनल सब्सक्राइब नहीं किया है तो प्लीज इसे सब्सक्राइब कर लीजिए, बिकॉज बाय द एंड ऑफ नवंबर वी शैल बी फिनिशिंग विथ ऑल द टेक्निकल सब्जेक्ट्स ऑफ मैकेनिकल इंजीनियरिंग, सो दैट यू मे हैव एम्पल अमाउंट ऑफ टाइम फॉर रिविजन एंड फॉर गिविंग द टेस्ट. अब टेस्ट सीरीज कौन से हमें बाय करनी चाहिए, इसके बारे में भी हम बहुत जल्दी एक वीडियो लॉन्च करने वाले हैं, जहां पर हम आपको बताएंगे कि कौन सी टेस्ट सीरीज अच्छी है और टेस्ट कैसे देने चाहिए, क्या स्ट्रैटेजी होनी चाहिए और क्या क्या हमें उसमें सावधानी बरतनी चाहिए अपने टेस्ट देने में, ताकि हमारा नेगेटिव मार्किंग कम से कम हो और हमारे जो नंबर आए उनको देख के हम डिप्रेस भी नहीं हो. ओके, सो इन द टू रोटर सिस्टम, फॉर एग्जांपल, वी आर हैविंग वन रोटर हियर and the other rotor is like this. Okay, such that they are connected by a shaft. Okay, this rotor is rotor number 1, this is corresponding to rotor number 2. This is having inertia I1, this is having inertia I2. Okay, so actually it has been seen that the node point, for example, is here. मान लीजिए हमारा node point somewhere यहाँ आया, तो कैसे vibrations का variation होगा? वाइब्रेशंस का वेरिएशन कुछ इस टाइप से, सॉरी ये इस टाइप से कुछ हमारे वाइब्रेशंस का वेरिएशन हो जाएगा. ठीक है, नोड से जितना दूर जाएंगे वाइब्रेशंस उतने बढ़ेंगे, और नोड पे वाइब्रेशन हो जाता है हमारा 0. ओके, से फ्रॉम द फर्स्ट रोटर द लेंथ ऑफ दिस नोड इज L1 एंड फ्रॉम द सेकेंड रोटर द लेंथ ऑफ दिस नोड इज L2. So and the total length of this rod is say L. So L is equals to L1 plus L2 will be the first equation, and we know omega n for this rotor is equals to under root st by I2, and omega n for this rotor would be under root st by I1. Okay, so there will be two corresponding omegas relating to these rotors. Okay, so and one more thing, omega for this would be equal to omega for this, because they are actually acting as one system. So omega of 1 is equals to omega of 2. It simply implies that under root st by I1 is equals to under root st by I2. So we will square these, squaring on both the sides, you will get st upon I1 is equals to st upon I2, and I have already told you that ST is the torsional stiffness, that is GJ upon L. So we can write GJ upon L1 and I1 would be equals to GJ upon L2 I2. So GG will be cancelled out. What we have obtained here is we have got L1 upon L2 is equals to J2 upon J1. It simply implies that length is inversely proportional to the J. Okay, so we will find out what is the value of L1 and L1 and L2 using this equation and equation number 1. Okay, so a very common question which is asked in such type of, so यहाँ पर एक जो बहुत common question पूछा जाता है, it is regarding find if number of rotors are equals to n, then number of node points would simply become n minus 1. तो ये भी हमें याद रखना है क्योंकि ये भी हमारा क्वेश्चन बहुत फ्रीक्वेंटली आस्क्ड क्वेश्चन है और ये पूछा भी जाता है. ओके, और एक और नोट पॉइंट है जो कि बहुत इंपॉर्टेंट है कि वो है द नोड पॉइंट्स आर क्लोजर टू दोज रोटर्स हुज इनर्शिया इज मोर. सो नोड पॉइंट्स आर closed to rotors having higher value of I. जिसमें इनर्शिया की वैल्यू हाई होगी वहां पर हमारे जो नोड्स होंगे उन रोटर्स के पास हो जाएंगे. Okay, now we shall discuss another important method to find out these vibrations, and that is called as Rayleigh's method. Rayleigh's method. Okay, so in Rayleigh's method, it is actually based upon the method of static deflection of the mass. This is also called as method of static deflection of mass. Method of static deflection of mass. And there are certain points regarding this method. The first point is it is only for natural vibrations. It is only for natural vibrations. Second is there should be no other mass. There should be no other mass. Only one mass should be present in the system. Third is equivalent stiffness is very difficult to determine. When we are unable to determine the equivalent stiffness, so equivalent stiffness is very difficult to determine. Okay, when it is very difficult to determine. Okay, say for example we have a mass which has been suspended from a spring. Okay, so for example this mass was initially here and now it has been displaced up to this point. This is mass m. So this is actually corresponding to the deflection. This is the static deflection of the mass, that is delta. Okay, and this was actually the mean position. Okay, this is the new mean position. Now S into delta would be equals to m into g, where S is the stiffness of this spring, such that delta is equals to mg upon S. Okay, so what we have done here is we are simply applying the balancing of forces. We are simply applying the balancing of forces. Now, if the spring mass system was in its natural length, even in the presence of mass, then delta is simply representing the difference between the points. Okay, so if the spring mass system was in its natural length, even in the presence of the mass, so delta is actually representing the difference between those points. Okay, so omega, the natural frequency formula for this type of system, is given by under root g upon delta, and it is actually very similar to under root s upon m. So we shall be using this formula under root g upon delta. Okay, now I will discuss some problems which are very, very important, and only those types of problems are being generally asked. The first type of problem that I will discuss is, okay, this has been given. A spring has been given of stiffness S1. This length has been given A. Okay, a mass is being hung from one end, say M. Okay, and this distance is actually B. Okay, and this rod is actually been given massless, that is M is equals to 0 for this rod. Okay, so we have to find out what would be the expression for the natural frequency of this system. So first I will draw all the possible deflections in the present system. Now we know that when the mass is hung from one of the ends, the deflection from some deflection would be found at this point, and because of this deflection there would be some deflection corresponding to this spring also. So this would be how we will get, say this deflection due to the spring was delta 1, and this deflection because of the static deflection of the mass is actually delta. Okay, the spring is S, this length is A, and this entire length is B. Okay, and let us say that because of this mass being hung, F force is developed in the spring. Okay, F is the amount of force which is developed in the spring. Now what we will do, we will take the moment about this point O. Okay, so we have mg into B. Okay, it will create a clockwise moment, and this is equals to F into A. This will create the anti-clockwise moment. Okay, so from here F simply becomes mg into B by A. Mg is equals to B by A. Now if we look in this triangle, say O P R, okay, in this triangle OPR, we are having this side as delta 1, this side as delta, this angle say theta. Okay, this is O, this is P, this is R. So we see that the triangles, say that this is M, this is N, the triangles OMN and OPR are similar triangles. These are similar triangles, and from the property of the similar triangles, this length actually has been given as A and this length actually has been given as B. So what we will say is delta 1 upon A is equals to delta upon B. This was from the similarity concept. So actually अगर force यहाँ पर देखा जाए, so what is this F? F is actually S into delta 1. S into delta 1 is equals to mg into B by A. Okay, so S into delta 1 is equals to mg into B by A. This was the first equation, and the second equation was this, such that we can write delta is equals to delta 1 into B by A. ठीक है, तो delta 1 की जगह यहाँ पर क्या लिख सकते हैं हम लोग? यहाँ पर हम लोग सब्स्टिट्यूट कर देंगे वैल्यू ऑफ delta 1 and we would obtain mg upon S into B by A का स्क्वायर. ठीक है, क्योंकि यहां से हमारा जो डेल्टा 1 की वैल्यू निकाली जाएगी दैट इज mg अपॉन S into B by A. तो डेल्टा इज इक्वल टू डेल्टा 1 into B by A, तो ये हो जाएगा हमारा डेल्टा 1 की वैल्यू ये है, दिस होल मल्टीप्लाइड बाय B by A, तो ये हो जाएगा B by A का होल स्क्वायर. सो ये हो गया हमारा डेल्टा की वैल्यू, एंड ओमेगा n would be simply under root g upon delta, that is mg upon S B by A whole square. So this would be the expression for the natural frequency of this system. Okay, so this was all about in this lecture. We come to the end, and in the next lectures also we shall be discussing about some very important numericals and also about the transmissibility of forces. So I request you to kindly pass on this information to your friends, that all those who are interested in learning the various concepts of mechanical engineering, they can subscribe to our channel, because we are not charging even a single penny from anyone, and I promise you that जब तक ये चैनल रहेगा तब तक पूरा का पूरा स्टडी मटेरियल हमेशा फ्री में प्रोवाइड किया जाएगा, सारे वीडियो लेक्चर्स आपको फ्री में प्रोवाइड किए जाएंगे, और आपको बस इतना करना है, आपको हमारे लेक्चर्स देखने हैं, इन्हें फॉलो करना है, अपनी प्रिपरेशन करनी है और अपने फ्रेंड्स और कलीग्स को भी अपने हमारे चैनल के बारे में बताना है. So in the next lecture we shall be discussing some more important numericals. So do stay tuned to our channel. Thank you so much.